So test number 2 covers C programming. Test number 3 picks up from test number 2. Its topic is pretty much interrupts and filters. So it'll cover timer 2 interrupts, timer 0, 1, 2, 3 interrupts, INT interrupts, and then filters, kind of like the last homework set. On the Here we are. On the test, you'll have access to the web, of course, so you don't have to memorize all the interrupts. You'll have this sheet. When the class had in-class tests, years back, like last year, you'd have access to this sheet, so you don't have to memorize all the hoops you have to jump through to get the interrupt to work. The test focuses on how to get interrupts to work, and it's got kind of goes in progression. There's a single interrupt having multiple interrupts working, and the most complicated one would be interrupts affecting interrupts. In general, for any given interrupt, I have to have the conditions for the interrupt. So, for example, timer 0, I can interrupt every n clocks, either based upon inputs through port A pin 4 or the clock, 10 megahertz. Likewise, timer 2, timer 3 can set the conditions for the interrupt. I have to turn on the interrupt, which is turn on, really turn on, honestly turn on, then global interrupt enable. And finally, once I do all that, that triggers the interrupt. When the interrupt happens, I have to have a flag get set. I've got to clear the flag at the end of the interrupt, otherwise I'm stuck inside the interrupts. So it's kind of a common theme on all the different interrupts, how you get them to work. One way to kind of go over that, let's look at some of the previous tests. I think about last semester. So on this test, again similar to this semester, it's the first test on interrupts. The first problem is just getting a single interrupt to work. Suppose I had the following code. This uses a timer 2 interrupt to toggle a pin, port C pin 0. The first part is kind of go through the code, see how it works. How fast is timer 0 interrupt? What frequency do you see on port C pin 0? And then, what happens if you comment out certain parts of code? With interrupts, they're very finicky. If you make any mistakes, it doesn't work. So this is kind of saying, well, what happens with the different parts of the code? Why are they important? What happens if you make a mistake and forget it? So the first problem is, what's the frequency of port C pin 0? To do that, I need to kind of go through the code and look at the setup. This guy right here is where you set up T2CON and PR2. What T2CON does is that tells you A, B, and C. I've got the number 8F, which is 10001111. So if you split up the bit pattern, A is equal to 0001, which is binary 1, meaning 2. Again, everything's kind of off by 2, off by 1. So A is 2. PR2 is 213, which means the B is 214. And then C is 11. 11 means 16. So that's A, B, and C. Multiply them all out, I get 438,000. No, I get some number. Inside the interrupt, I'm counting mod 64. So we'll just be counting 1, 2, 3, 4, 5. Every 64th interrupt I toggle. So the net number of clocks between interrupts is A times B times C times 64. So it gives you a total of 438,727 clocks between toggles. The frequency then is 10 million divided by 2 times n, because I need 2 toggles to get a cycle. The nominal case is 11.4 hertz. Now what happens is as I delete different parts of the code, if I leave out the first part, if I quit counting mod 64, then what happens is I just have this count. Count is never changed. If count happens to be 0, I will toggle every interrupt. And so it is this frequency times 64. Again, rather than toggle every 64th interrupt, I toggle every interrupt. So it becomes that times 64, 730 hertz. If count is not 0, it never changes. If it never changes, it never toggles RC0. If it never toggles RC0, you get 0 hertz. So that's what happens if I leave out this part of the code. If I leave out the second block, if I leave that out, I'll interrupt just fine, except I don't actually do anything. So if I don't ever do anything, RC0 is never changed. It'll be 0 hertz out. If I forget this line of code, in that case, what happens is I'll trigger the interrupt, toggle RC0, get back in. It'll immediately say, hey, the flag is still set, trigger the interrupt. Go through it, come back out. Then it immediately say, hey, the flag is still set, trigger the interrupt. So if this is set, I'll actually interrupt every 50 clocks, ballpark. The toggle then is every 50 clocks times 64, gives you 320 clocks. No, 3,200 clocks. So then n is 3,200, and the frequency is 1562 hertz, rather than 11 hertz. And you're stuck inside the interrupt, always interrupting. Let's see. If I leave off this section of code, it still runs. I'll still be interrupting. I'll still be toggling port CPIN 0. The problem is I have no idea what the frequency is, because it depends upon what T2CON and PR2 are initialized to. It'll be whatever it was last time you set them, pretty much. So it's working. I just don't know the frequency. If you forget to turn on, really turn on, honestly turn on, it's not on. If the interrupts aren't on, port CPIN 0 never toggles. And in the main routine, if I don't do anything in the main routine, the interrupt doesn't care. The interrupt does all the work. Every n clocks it interrupts, it counts. Every 438,000 clocks, it'll toggle. So what happens in the main routine doesn't matter. This is the same. That's one of the powers of interrupts. Do whatever you want in the main routine. Drive the LCD display, read the push buttons, whatever you want. That's not going to affect this frequency. So that's one problem, just having a single interrupt working. A little more complicated. I can get multiple interrupts running at the same time. And I can set it up so interrupts really don't affect each other. I'll just have timer 0, interrupt, and toggle RC0. I'll have timer 1 interrupt and toggle RC1, timer 2, timer 3 interrupt, toggle RC2. They really have no impact on each other whatsoever, so treat this as 3 separate problems. For timer 0, if I want to have a 0.153 hertz square wave, 5 million divided by, 10 million divided by 2 times frequency gives you n. N is 32 million. 32 million is too big. I can't implement that with a 16-bit counter. With a 16-bit counter, the highest I can count to is 65,000, so I got a problem. I can throw in a prescaler. If I do a prescaler times 65,000, it's still too big. So what I can do is, rather than toggling every interrupt, I can toggle every other interrupt. So that's what this is. I just have a counter. I'm going to count 0, 1, 0, 1, 0, 1, counting mod 2. On 0, I toggle, otherwise skip out. So every second interrupt, take this number divided by 2, divided by 256, gives 63,827. That I can do. So every 63, when I timer 0 interrupts, interrupt again in 63,000 clocks. Every other interrupt I'll toggle. I'll interrupt actually every 256th clock. So there's my prescaler times 2 times 63,827 gives you 32 million. And every time it's time to toggle, I toggle RC0 and acknowledge the interrupt. That's the first one. The second one, 7.22 hertz, is 692,000. Again, that's too big. I can only implement numbers up to 65,000 with a 16-bit counter. If I throw in the maximum prescaler for timer 1, its max prescaler is 8. and I still need another counter. So let's just count to 2. So 692,000 divided by 8 divided by 2 winds up being a number less than 65,000, 43,282. So here's when I interrupt, sets up the next interrupt, and 43,000 counts later. Every other interrupt I toggle and interrupt every 8th clock. And then every other interrupt I'll toggle a RC0 and acknowledge the interrupt. The last one is 86.79 hertz. 5 million divided by 2 divided by frequency is 576. That I can do. So whenever I interrupt, I'll set up the next interrupt, 576 clocks in the future, toggle RC2, acknowledge the interrupt, exit. So there I've got 3 interrupts running at the same time, each at a different frequency. Problem 3 is a little more complicated. I want to measure time and generate frequency, so I actually have 2 interrupts running at the same time. I'll have, in this case, timer 2 measuring time to 1 millisecond. If the door is left open for 30 seconds, I'll turn on timer 0. Timer 0 will output a 300 Hz square wave. That's kind of a problem that you do in 401, except you do with the 555 timer. I can do it with the microprocessor as well. To do that, again, I don't have to write the whole code on the test. You don't only have 2 hours to do it. All I really care about is the interrupt initialization, the interrupt service routine. That's really all I care about. The main routine can do whatever you want. The interrupt will do all the work. So to set up timer 2 for 1 millisecond, I set A equals 10, B is 250, C equals 4. You have many combinations that do that. Here's one option. To set up timer 0 for 300 Hertz, this sets up prescaler to 1. On a timer 2 interrupt, every millisecond, time passes. What I'm going to do is check the push button, or check the door. If the door is open, can signify door is open as RB0 equals 1. If the door is open, 1 millisecond's gone by. Keep counting and clip at 30 seconds. If I don't clip, then it's going to wrap around every 65,000 clocks or counts. This stops wrap around. Count to 30 seconds. When I get to 30, stop at 30. As soon as the door closes, reset the timer to 0. So I've got the doors closed, I'm at time 0. Open the door, it's counting up. Close the door, go back to 0. Open the door, counts up. Close the door, goes back to 0. Open the door, leave it open. 30 seconds later, time gets to 30,000 milliseconds. When I get to 30,000, that turns on timer 0. So one interrupt is turning on the other interrupt. At 30 seconds, I'll toggle RC0, saying the door has been left open for 30 seconds. I'll do that if time is equal to 30,000. And I'll also interrupt at 300 Hertz. This number is 10 million divided by 2 divided by frequency. Gives you that number. Once the door closes, I'll turn off the alarm and acknowledge the interrupt. So here I've actually got 2 interrupts running. They're working together. Timer 2 measures time. When I get to 30 seconds, timer 0 turns on. And there's many ways to do it. This is one way. On this type of problem, it kind of pays to sit on your hands for like 2-3 minutes and think about how you're going to solve it. I can measure time with timer 2. When I get to 30 seconds, I want to turn on timer 0. How do I do that? One way is use a global variable so that one interrupt talks to the other interrupt using the variable time. When time gets to 30,000, I'm at 30 seconds. That's one way. Other ways as well. Problem 4 is using timer 1 capture to measure the frequency of a square wave. Again, this is kind of similar to a homework problem we had. In this case, I've got to turn on timer 1. On timer 1 capture, if it's set up, every rising edge, I'll save the time. That's time 2. Remember the previous rising edge. And the number of clocks between edges is the period. That's the difference in time. That's the interrupt. The interrupt changes n. Every rising edge will tell you how long was the last rising edge. In the main routine then, I can calculate the frequency. Oh, this is the temperature sensor. Okay. Once I know the period, I can calculate the resistance. Once I know the resistance, I can tell you the temperature. So in that case, in the main routine, I know the period in clocks. I can tell you, I know n. I could then solve for R. Given n, I can find R in ohms. And given R, solve backwards, I can tell you temperature. So this would be the main routine. I know n from the interrupt. I calculate R. Given R, find temperature, and plot the temperature. And the resolution. When I do this, what I'm asking is, what's the smallest temperature change you can see? Well, the smallest time change I can see is 1 clock, 100 nanoseconds. So one way to do that is at 25 Celsius, calculate the resistance, calculate the period in milliseconds, and what n is. The smallest change in n I can get is 1 clock. Go from 561 to 562. That changes the period slightly, changes the resistance slightly. The difference is the resolution in ohms. I can measure the resistance to 0.007 ohms. The difference in temperature, calculate that to T, is the difference between 25 and 24.9998. So I can see temperature to 0.0001 ohm. That's one of the powers of timer 1 compare and capture. If I can measure time to 100 nanoseconds, I can measure temperature really, really accurately. And the last problem was due the following Monday. Program your PIC board with either problem 4 or problem 5. That was from last semester. Let's do one more. Maybe from here. Okay, similar first problem. This one was using also timer 2. Could be timer 0, 1, 2, 3. Same idea. If you don't set the conditions, or if I don't enable the interrupt, what's going to happen? Generate 3 frequencies, same idea. Here's another one where I've got multiple interrupts. This is a bouncing system. When I press a button, I want to play 220 Hertz for 500 milliseconds, precisely. In that case, I've actually got 2 interrupts running at the same time. I'll detect the rising edge with an INT 0 interrupt. When that happens, I'll turn on 2 timers. One timer is half a second. The second timer is 220 Hertz. So for the INT interrupt, I'll look for the rising edge. The timer 1, if I use that for frequency, 220 Hertz corresponds to 22,000 clocks between interrupts. And half a second is 5 million. So to do that, what I would do is on a rising edge interrupt, that's an INT 0, I'm going to set RC1. Call it this timing diagram. RC1 gets set. Half a second later, it gets cleared. The way I do that is I'm going to have timer 0 kick in half a second later. For that to work, I need 5 million. I can't do 5 million with a 16-bit counter, so I need a prescaler. If I max out the prescaler, 256 times 19,000 is 5 million. 19,000 counts in the future will be half a second. At that time, trigger a timer 0 interrupt. When timer 0 kicks in, I clear RC1. So that's this guy right here. Every time I see a rising edge, I output a half-second pulse on RC1. What timer 1 then does is every 220 Hertz I toggle, which is this guy, 220 Hertz. But I only toggle when RC1 is true. Otherwise, I clear RC0. So what happens now is on a rising edge interrupt, I turn on RC1, trigger timer 0 interrupt half a second in the future, then it clears it. While RC1 is high, RC0 is toggling at 220 Hertz and then goes quiet. So again, I've got 3 interrupts working at the same time. They're all kind of coordinating with each other. A little more complicated. And on this test, we have digital filters as well. This one is given a filter and a sampling rate. Come up with the digital filter that's equivalent to it. Again, just do an S to Z conversion. I've got a 0 at -3 in the S-plane. In the Z-plane, it's e to the ST. I've got a 0 at 0.97 in the Z-plane. I've got a pole at -15 in the S-plane. Convert to the Z-plane as e to the ST. That's a pole at 0.86 in the Z-plane. -30 goes to 0.74. So that sets the poles and zeros. To set the gain out front, K, just match the gain at some frequency, typically DC. At DC, G of S has a gain of 0.2. Pick K so that G of Z has the same gain at DC. And you wind up with K is 0.24. So here's the filter. And for B is if I had a filter, a different one just so we have a common starting place, implement that in software. The trick again is multiply it out, cross multiply, solve for the highest power. This tells you that y of k plus 2 minus 0.9 y of k plus 1 is 0.2, x of k plus 1 minus 0.3 x of k. Shift everything by 2, so I no longer deal with the future value of y. Shift everything by 2, bring everyone else right. There's your program. So I need to set it up, remember the last 2 values of the input, remember the last 2 values of the output. The current input is the current input, and the current output is this equation. 0.9 times the previous output plus 0.2 times the input 1 sample ago minus 0.3 the input 2 samples ago. So that's the beauty of the Z-plane. I can implement it exactly. And on this test we had an analysis, and you might expect that on this test as well. If I have a filter in the Z-plane and the input's a constant and a sine wave, find the output. And for this, use superposition. If x is 4, I'm at DC, s equals 0, z is e to the st, or 1. This is the gain everywhere. What's the gain at DC, or z equals 1, times the input as equals 1, and I get 56. So there's the DC term. At 7 radians per second, x is 5 minus j6, real is cosine minus j is sine, s is j7, z is e to the st. Analyze, I get a complex number. Real part is cosine minus j is sine. And the total answer is DC plus AC. So that's what you can expect on the test. On this one, I won't do like last semester we have the take-home problem. It'll just be interrupts and Z transforms.